So today we are going to finish the talk about the recurrent neural network, RNN. And then, as you already know, I announced the final project. So I'm going to explain what the final project is going to be. And that's the today's plan. So first, I'm going to finish the RNN explanation so that you can finish your this week's assignment, which is which generate new music, not the random music. So we are going to we are able to now we are able to make a new song. And then the second part, I'm going to explain the final project, the competition. Okay, let's go to the learners. And there are lots of things. I'm going to start with the. Okay, yeah. Let me say you something about the reading materials. This is written in some blog, and that's my blog. And actually, that's a paid site. But when you click this button, you can read it freely because that's a free link. But if you go to the other site from there, then you might be asked to participate. You might be asked to pay money, but please do not pay money. Yeah, and just read the materials that I made a link. So today's RNN is about the first reading material, and the third reading material. These two are really short, but this is the whole basic of the RNN. I also wanted to talk about the reading material too, but I decided not to go over it because that's a little bit beyond your current knowledge of the Python. So I'm gonna stop. So if you go to the reading material 1, it is written in 3 different languages. So I first started writing in Korean, and then I just Google translated to the English, and I found that yeah, there is another translation. So I tried to make it a Japanese, but I don't know the Japanese at all. So if you already finished reading this one, yeah, that'll be fine because this is just the how can we make the shape right for the RNN. So let's go to the simple RNN collab. There are 2 collab links, but I'm going to talk about the simple RNN collab though, which is on the 3rd. Okay, connected. So as usual, we import NumPy and import TensorFlow. And it says there are 3 different types of RNN network. The most simplest one is the simple RNN. And even though I'm just explaining what the simple RNN means, but you can always expand you can always change your network to LSTM or GRU. The difference between these 3 RNN layers are there are some mathematical formulas inside the cell, and the difference between these cells make the 3 different RNN layers. Other than that, they are basically they works in the same way. So let me define RNN. So it's TF, keras, layers, and simple RNN. And I write number 1. And this is the really confusing part because you already know what the dense layer means, and you already know what the convolutional layer means. And usually in the dense layer, the number we put in the first place is the number of nodes in that layer. But the RNN, for the RNN, it is not the case. So we just take this number as given, and we will see how can we change this number, and we will see what this number means. So first we define a simple RNN layer, and then call it as RNN. And in order to see what's going on inside the RNN, we need to make a data set. So it's an MP array, and for I is in range 20, so it will start from 0 up to 19. So the total number of numbers will be 20. And then I made it to the float, and there is a reason. I started with just the integer variables, but for some reason the simple RNN cannot take the integer input, so we have to change it to a float. So, and then let's take a look at the shape of the x dot shape by printing it, and it says 20 comma nothing. That means it's a one-dimensional array with 20 numbers in it. So we can actually see what's inside. It's 0, 1, 2 up to 19, and it's a float because there is a dot. And then let me just try to put this number into the RNN layer. Then you will get the error message, and that error message is important because it says the simple RNN is incompatible with the layer, and expected dimension is 3, but it found just one dimension. And we understand that why this layer found the just one-dimensional array, because we put the one-dimensional array, and the full shape received is 20 comma. So that's what we did. So the first problem of that is we should provide data with three-dimensional data set to for the RNN to work. So I'm going to just reshape the 20 numbers. The reshape is you specify the numbers. So we have all 20 numbers, but I'm gonna make it 2, 10, and 1. Then total number is still the same. And before I run it, I'm gonna show you what's inside the X after reshaping it. And it's 1 to 0, and no, it's 0 to 9 and 10 to 19, but the shape is different from the previous ones because we reshape it. So to see the reshaped form, it's 2. So basically, you may think that the whole data set is just 2 songs. And then the second number is 10. That means in each song, there are 10 notes. And in each note, 10 chords. And each chord, we have just 1 note. So that's the meaning of 2, 10, and 1. And let me run this code. Then we don't know what this number is, but we just we did not get the errors. We make it to work. So the output shape is 2, by 1. So input shape was 2, 10, and 1. The output shape is 2, 1. So there might be some relationship, but we don't know the exact relationship yet. So let's keep going. So input dimension is the first one is the number of examples. That means the number of songs or number of music. And then the second number is the time steps. And the third number is number of features. If you think about this as a music, then it will be 3 at one time, and there is another 3 note at the other time, and so on. So we can run this one. Okay, so now we know the shape. And actually, there are 2 options you can put into your simple RNN. So first number, I'm going to call this first number as the hidden dimension. And the hidden dimension is set to 10. It was originally 1, but you can change it whatever number you want. And there are 2 options. The first one is return sequences, and the second one is return state. And this is the arguments that can take the booleans. So you may set it's a false or it's a true. And if you think about the all possible combinations, there are 4. And the default is all false. So all false cases will be called RNN1. And then I change 1 by 1. So one is true, the other one is false, the other one is true, and true, false, and true, true. And I call them RNN 2, 3, and 4 respectively. And we will see what these what kind of outputs these numbers will produce. We still have the same inputs, 2 by 10 by 1. And let's make the 4 different RNN layers. And then RNN1X. So just focus on the shape of the output of the network. So it gives you one tensor, and that one tensor has shape of 2 by 10. And it's a result of return sequence is false and return state is false. Now let's move on to the return sequence is false, but return state is true. So it is the case of the RNN2. When I execute it, we have a list. Before, we have just one tensor, but now we have a list. And inside the list, there are 2 tensors. So one is up to here, and the other one is here. And look at the shape of each tensor. It's 2 by 10, and it's 2 by 10. And if you compare these numbers with the previous one, actually they are all the same. So it's strange. Even if you said the return state is true, it gives you exactly the same outputs twice. Okay, let's keep going. Now the return sequence is true, but return state is false. This is the third case. When I run it, I have lots of numbers. So the first one says it's 2 by 10 by 10. And that's it. There's nothing more. So in some sense, I think the RNN3, if you understand the RNN3, which is return sequence is true and return state is false, that return sequence is true gives you all the information that you need, actually. But depending on the situation, so yeah, we need a version of the RNN1 or RNN2 or RNN3. And there is one more thing, RNN4. So let's move on to the RNN4. So RNN4 will give you another list because it has 2 elements in it. So the first one is 2 by 10 by 10, which is same as the return sequence is equal to true, because the RNN4, still the return sequence is true. So whenever you want it to return sequence is true, then it will return, yeah, this one. And then it also said the return state is true, and return state is true gives you this part. Okay. So there are 4 different RNN models. So RNN 1, 2, 3, and 4, and one, both one is false. Its return sequence, its return state. And the second one, I said return sequence is false and state is true. And this one, this is true and this is false, and all are true. So let me go back to see the shape. Okay, this is 4. Okay. So it gives me 2 by 10, and it gives me 2 by 10 and 2 by 10 in a list. And it gives me 2 by 10 by 10, and it gives me 2 by 10 by 10 and 2 by 10 in a list. So we can see from here the RNN3 and RNN4, the return sequence is true in both cases, and it actually returns the whole sequence. So that's the meaning of why we have this shape. That's the meaning of the return sequences. And if you see the sequences, so let's focus on the 10 in the second place. And actually, that means it gives you 10. And of course, inside this yet 10, there are 10 values because of this. And actually, return state is just the final one. That is the state. And if you did not specify the return state is true, and this one is just the output, the last one. A little bit confusing, but let's go to, so yeah, just keep in mind, you are going to have all the corresponding time step outputs when you set the return sequence is true. So remember, RNN 1, 2, 3, 4. So RNN 1 gives you just the output, but actually that output is actually equivalent to the final state values. But RNN 1 says return sequence is false and return state is also false. So it does not return the state. It just returns the final output. In RNN2, we specify that return sequence is false, so we will not get all these 10 sequences, but return state is true. Then this RNN2 will give you the original output, but actually the original output is always equivalent to the not always equivalent to the state, but in the simple RNN case, it is always equivalent to the state. So RNN2 gives you, the first one is the output, and the second one is the returned state. Now RNN3 is return sequence is true, but return sequence is true, but return state is false. Then it just returns the whole output sequences. So in RNN3, we have whole output sequences, and it does not return the output. And you may think that this is a little bit strange, but the last elements in the return the sequences is actually the output and also the state. Now the RNN4 is return the whole sequences and also return the state. Then RNN4 returns the whole sequences and then the final state. But this one, this one is actually equivalent to this one. Yeah, that's right. Okay, so this is just the beginning of the RNN, and we still do not know what's inside the RNN, but I just explained what will be the output shape. Okay, so I'm going to fix the random seed so that we can actually compare the numbers. So here I'm going to make the H dimension is 3. So H dimension is the first number we need to put in the RNN definition. And then we have return sequences might be true or false, and return state might be true or false. And then there are 2 more lines, but this is just to set the random numbers to be a specific number so that we can, every time we run the code, we will get exactly the same result. So again, the RNN 1, 2, 3, and 4. And when I run the RNN 1, now the shape is 2 by 3. So the first 2 is just the number of songs. And why we got 3 here is go to the, so in the original format, in the input, this is the first song and this is the second song, and we have 10 time steps. So it's 10, and inside each time step, we have just 1 note. And this is the same for the second song. So I'm going to erase the second song part. And inside the RNN, you are going to put all these things, but there is some mechanism, and it will produce the output. And this, if you want to see the only outputs, you have to set the return sequence is false and return state is false. And this output has 3 dimensions because I said HDIM is equal to 3. So that's the meaning of the dimension of the RNN definition. So it's RNN, and the first number is the number of output dimension. It's the not the number of dimensions. It's the output dimensional number. So this is the RNN1 and RNN2. When I run it, I have 2 by 3 and I have 2 by 3. And actually these numbers are equal to these numbers. You see, it's 0.8, 0.99. So here is 0.8. And since we have two songs, the first 3 number is for the first song, the second 3 number is for the second song. And here, the RNN output for the first song and for the second song. And this is the returned state for the first song and the second song. So return state means in addition to the output, it will return the last states, which is actually the same. So you have one output and you have a state. So when I run RNN3, which set to return the sequence is true and return the state is false. And it returns 2 by 10 by 3. That means this RNN actually have the first state, the second state, third state. So actually, it will put all these things, and the final state is actually the 10th one. So return sequence is true, you will get all these 10 outputs. And the final output is called a state, and that final output will be an output. Now RNN4. RNN4 return sequence is true and return state is true. So that means the whole sequences will be returned and the final state is also returned. So we have 2 by 10 by 3, which is the whole sequences, and 2 by 3, which is a state. Okay, this is the basic structure of the RNN, but inside that layer, actually, there is a function. So I'm going to explain how can we calculate all these 10 sequences or the outputs or the states in a different column. So it's simple RNN calculation. So let's go to the simple RNN calculation and connect it. So import NumPy and TensorFlow. And I'm going to make just 3 number. So I'm going to call it as DT. So DT is just 1-dimensional 3 numbers. And you already know that if you put the DT in this form, you will get an error because the shape does not match to the input of the RNN. So there is an explanation for the Medium website, which is also linked in your Learn Us. So let's first make a simple RNN layer with 2 hidden dimensional outputs. So that's the meaning. So I intentionally changed the numbers. So there are 3, the time step is 3, and the number of nodes is 1. At each time step, we have just 1 node. And we define the output of the RNN is the 2. I mean, not the number of outputs, but the output, the dimension output number is 2. And I need to make this DT with some new commands because it requires 3 dimensions. So it says MP new axis is on the first dimension. It was originally 1-dimensional, but I'm going to push a new dimension in the first place. And then in the second place, I want to keep all these things. So I want to keep these 3 time steps. And then on the third axis, I'm going to add new axis. So once you do that, the X looks like this. And if you see the shape, it's 1, 3, and 1. So originally the DT shape was 3. It was just 3. But the MP new axis put 1 in the first dimension, and the third new MP new axis put another dimension on the third place, so that the whole shape of this data is 1 by 3 by 1. And we can put the number inside. Then we get just 2 numbers. So now I'm going to explain how these two numbers are calculated. So this is the another, this is just the definition of the TF, keras, layers, simple RNN, and the units is the number of the HDIM was the unit. And I said return sequence is true, but I did not specify the return state is true. So the default is return state is false. And in order to simplify the explanation, I said the activation is linear. So there is no activation. It is just a linear combination of the whole numbers. And then I said, yeah, some numbers will be 1 and some numbers will be initialized as 10. So that is the definition of the RNN. And when I run this one, I get 1 and 1, and 22 and 22, and 443 and 443. And let me explain one by one. What's inside the RNN is this function. So here, WX is this one. So you may think that WX is some parameters that will be applied to your original data set. And there is another matrix of parameters, which I call WH. The H means hidden. And there is another hidden state. And note that the index, so in order to make the first outcome, the H1, we need X1, but we also need H0. And H0 is set to 0 by default. So this is the number. So X1, I'm going to show you one by one. So X1, X2, X3 comes from this one. This is 1, 2, and 3. So RNN first, the first operation on the RNN, just take the first number 1 here, and then set the hidden state is equal to 0. So why these? There are only 2 numbers. That's because we set the hidden unit is 2. So that's why we have 2 numbers. And then in order to calculate the first hidden state, H1, we need this formula. So the 1 is from the data, and this one 0, 0 comes from the hidden state. and then multiply the already defined matrix. So I said WX is 1 and WH is all 10. So if you calculate these numbers, you will get 1 and 1. Because these 10, this matrix with 10s is multiplied by 0. So all this thing is 0, and you'll get 1 and 1. And this 1 and 1 will be H1. That will, so let me draw it again. So we put 1, 2, and 3. And in the first place of the RNN, it will take 1. And there is a hidden state, H0, which is 0. And then for this one, WX and WH is already defined. So you may think that it, at the first place, it is set as random, but I intentionally make to this one is 1 and this one is 10, so that our calculation is simple. So first, take 1 and 0 and do some calculations, and it will produce 0. It will produce 1 and 1. And then the number 2 goes here, and the hidden state goes here. And WX and WH still remain the same, and do the computation in this way. So now XJ is 2 here, and WX is still the same, and WH is still the same, but now we have a new state, which was calculated in the previous step, which is H1. So by applying the H1, you will get H2. And you can do the calculation. So it's 1 times 2, 1 by 2. I mean, 1 times 2, and there is a 10. And since this is a matrix multiplication, you will see that after doing all this, and it's going to be 20. So we have 22 and 22 here. So now H2 is 22 and 22. So it produced, I might say, here, 22 and 22. And this one is also 1 and 1. Now with this number, we can do the same thing with 3 and 22 and 22. And it will also produce some number, and that number is calculated by this formula, and H3 is 443, 443. So it's 443, and it's 443, and it also produce 443, 443. So this is the actual calculation inside the RNN layer, and it has its own names. So this one is called a sequences. So when you say the return sequence is true, it will give you these numbers. And when return state is true, it will give you not this. It will give you it gives this number. So that is the return sequence is true. And if you did not specify anything, it just gives you the final output. So you can, but in since I wanted to explain it with very easy calculations, I intentionally said the activation is linear, but in the original version, the activation is not linear. In the original version, the activation is something like 10H. Yeah, it's from the trigonometry, but don't worry about this function. This function is just the transformation of the number to certain range, and that range is +1 to -1. So if your x is anything, you will always get a number between -0 and -1 and +1. But here we get a number bigger than 1 because we said the activation is linear, so it ignores the 10H activation and do these calculations. But in the usual example, the 10H function will be applied to this linear combination so that the numbers are not as big as this. So in the previous collab, I think, yeah, I have a question, but yeah, in the previous collabs, it is just you don't have to worry about what was the option, but you will see all the numbers is between -1 and +1. Okay, question. No. Today's assignment is composing a music like last time, except that we are going to use the RNN to make it. So that's why you have to understand the RNN. Okay. So in the previous assignment, it was a random generation. So you just put the random numbers and you get a music, which is not so beautiful. But this time, we have a sequence of notes and then take each notes with the RNN network, and then it will produce beautiful music. So let me pause, and if you have any questions on the RNN, yeah, ask me. Oh, I have 3 hearts. Yeah, good. That means you understand. So we have the collapse, and we have the medium, the blog post that I tried to explain. So even if you didn't understand what I'm saying so far, you can always go back to there and read it carefully. Oh, yeah. So probably, yeah, the students is going to send lots of hearts to all the participants. Okay. Yeah. Yeah, there is a reason. So yeah, this is a very good question here. Why we wanted to, sometimes why we wanted to return sequences, or yeah, sometimes why we just wanted to the final outputs. So that's very good, please. That's a very good question. So I'm going to explain. So for the state, so RNN is said to have a state, and usually it is called a hidden state. So let me explain the hidden state in this way. When you listen to a music, when you first hear the first note, you can feel almost nothing. Yeah, just one note, and played another note, another note, and you can feel that, oh, this song is going to be happy, or this song is going to be sad. So as you listen to your music, you realize, yeah, the mood of the music. So that is the hidden state, in my sense. So when we first process the first data, x1, which is the first note, since we don't know any state, so we just say that, this is 0. We don't know anything about that. But when you process the first note, it will produce, well, it might be 0.1 or 0.2. Yeah, it depends on, I don't know. I don't know how can I say that, but it produced some mood. And then for the second note, it will update the mood and update the mood until the final time step. And in some cases, you just wanted to classify music. So for example, let's say I have a bunch of Bach's music, and also I have a bunch of Mozart's music. And then my problem is just to listen to the music and classify whether it is composed by Bach or whether it is composed by Mozart. How can you do that? When you listen to music, we can almost always classify, this is the Bach style and this is the Mozart style, because they are very different. But in the RNN, in this only final state. So by calculating and updating the state, you can classify it's from Bach or it's from Mozart. But in our cases, we want to mimic the Bach or we want to mimic the Mozart. So by just knowing the final state is not enough. We wanted to see the intermediate states. So how can you see these all intermediate states? That's by setting the return sequences is true. So that's the way we see the intermediate values, so that I can use, say, I don't know, the bar. So it's always sol, sol, la, la, sol, sol, mi. And my network see the sol, and then it says, oh, okay, maybe it's 0.2. And then, of course, pass this 0.2 to the next one. And then the next sol see this 0.2 and then do some calculations and produce, okay, this is 0.3. And that 0.3 is passed to the next one. And here is a la. And since there was a previous information, so it was a sol, sol, la, and maybe, the next one is going to be la or something. So that's the way we make music with the recurrent neural network. So how can you do that? Actually, we are going to put sol, sol, la, la here, and then compare these things. Of course, there will be some mechanism to convert this number into the note, but the TensorFlow will do that for you. And then to minimize the error of the predicate value and the true value. So how can you minimize it? By adjusting the WX and WH here. So that is the whole idea of the recurrent neural network. So it is very important to keep all the previous informations, but in this simple RNN, it is not so good to memorize the older informations. So the people, the smart people, make something more. So we said the simple RNN, but there was another layer called LSTM. and it's a long, short-term memory. MEO. And with some mathematical formulation inside this node, amazingly, this layer have two hidden states. So simple RNN has just one state, which can be even though it was one state, it can have several. So it is a vector, but the long short-term memory have two hidden layers. So one is for long, and one is for not. Well, we can call it short. So pass two hidden layers. That's the difference between the simple and LSTM. And this LSTM is good, but it's a little bit complicated. So there was another genius guy. I'm not sure if he's a genius or not. He made another unit, so-called it's gated recurrent. I don't remember. So let's Google it. Who made the GRU? So GRU is a gated recurrent neural network. I don't want to see it. So let's go to the Wikipedia. So gated neural network, and inside here, the formula is much more complicated, but still, it's some linear combination and some activation functions. And amazingly, this is made by the Korea. So I think he's a professor in the United States, and he is a computer scientist. So he made it in 2014. So people use it. So that's the GRU. So how can you use it? We just changed the name of our definition of the simple RNN by GRU, or just change the name of our simple RNN by LSTM. Then TensorFlow will handle all the other things. So that was a good question. Okay, now I'm going to show you how can you generate a music. And since this is not shared by you, I'm going to share with you. Okay, copy the link, and I'm gonna put it in a chat. So you can copy and paste it in your browser, and you can see the TensorFlow Music 21. And this is the actually answer collab for this week's assignment. But I'm gonna change a little bit. So first, we wanted to install all the necessary libraries to play the music. So do you remember the Muse score or XVFB, all these things? So I just copy and paste the previous notebook into just one cell so that we can use. And then we import NumPy, Matplotlib, and TensorFlow, and we also import Music 21. And there are two functions: extract notes, which we defined in the last lecture, and there is also a function data to music. but there is a minor modification in extract nodes function. It's get elements by class nodes. It was originally, I think that it was x recurs dot node, but when I tried to run it with different songs, I got an error, so I just make a little adjustment. So I don't think there will be no errors. And then, as usual, we take a song and then extract just one part, and then set it to vocabulary and F1, F2. And this is actually the last week's assignment. So we make MP random choice and then do something. So this is the randomly generated music. So what we are going to do today is just to replace this one line, the output, with our TensorFlow model. So the older lines before the random choice is just to extract the information from the music and then prepare for the TensorFlow. And then after that, we are transforming the TensorFlow output into the music. And between these two, we set just the MP random choices, this one. But since we learned the RNN, we can use the RNN to produce the real music. So let's see the data set first. A data set was defined here. It is already applied. The data set is already applied by the string lookup function. So string lookup function. So we have 64 nodes. It's 5, 8, something. So it corresponds to some values and some nodes. And as I said, the RNN layers cannot take the integer values. So I'm going to change it to float value. So in order to do that, I did this, numpy and as type MP float, and x is basically the same number but it's the data type is float now. And then we know that in order to put the music inside the RNN, we need 3 dimensions. So we intentionally add first dimension, MP new axis, and then intentionally add the third axis, MP new axis. So now the shape is 1 by 46 by 1. Now I'm going to make a very simple model. It's a TF-Keras sequential. And then first layer is TF-Keras layer simple and 1. And I set the return sequence is true because every time step I want to get a hidden state at every time step so that I can compare all these numbers with the original music, and then to try to minimize the error. So that's the first layer. And then the problem is what it produces is just a number, not a node. So in order to make that number into a node or something similar to a node, we need some idea. How can you do that? So RNN actually does not care what the input is and what the output is. It just take all the numbers and produce lots of numbers. That's just a computer. But since we started with nodes, and we make a vocabulary from the nodes. So maybe suppose that we have only say do, re, mi, fa, sol, la, si. 7 notes in the same octave. But in music, it can be sharp or flat, or in the one above, one below. And since this is just a 7, I'm gonna make another dense layer here. And the output of this dense layer is just 1, 2, 3, 4, 5, 6, and 7. And this 7 number gives me the probability that the information from the previous one is do or re, mi, fa. It just gives me a probability. So we are gonna select the high probable nodes from each time step. So this is the output for each time step. But we just need to specify the dense layer as the number of vocabularies. So that's why I said TF keras layers dense, and the number of nodes in the dense layer is F1 get vocabulary the length. In this way, we can always match the number of nodes that we are gonna use. But there is a problem in this way, because the get vocabulary has 0 and 1. The 0 means the empty, and 1 means unknown. And our actual nodes starts from 2. So actually, there are 2 extra nodes, but it's okay from now, for now. But we will. I'm going to tell you how to handle that. So this is our model. So from the simple RNN layers, we are going to put 46 nodes, and it will produce 46 outputs. And that 46 outputs, the reason why I get 46 output is the recurrent sequence is true. So that's the reason why I get the 46 outputs. And then that 46 outputs will, and each output will turn into a possible 7 numbers, but not 7, but the get vocabulary numbers. So that's our model. And in order to run, we need to compile. And compile needs at least 1 information, but usually we give it 2. The first information that must be provided is what is the loss function. And what is our loss in our case? So we want to make our music as the original one as possible. But our output, here we set it as a probability. But actually, there is no guarantee that this one will be a probability, but our y. So this is in some sense, this is the predicted value from the model. This is the prediction. And our actual y is just, something like 3. Maybe, 4. Just a note. So what kind of loss functions can we use in this case? Remember that? So this is the classification problem, and there are 3 cross entropies. The simplest one is the binary cross entropy, and it always detects whether it's true or not. And the second one is the sparse categorical, the categorical cross entropy. But in order to use the categorical cross entropy, you need to make your output, your y, to be something like do and or zeros for the other nodes. So you need some manipulation for the y. But in this case, we have just numbers. So that's why we can use sparse categorical cross entropy here. So it's TF Keras losses sparse categorical cross entropy. And from logic equal true, by setting the from logic equal to true, you can be sure that all the numbers from the dense layer will turn into a probability. So that's the compile section. And then what is your X and what is your Y? I want to make my song to be exactly the same as the original one. So X is X and Y is also X. And let me see whether it is good or whether it is working or not. So the epoch is, oh, I did not run this part. So run the model, model.compile, and model.fit. And it gives me, yes, it is working. So yeah, let me see, how can we predict? So X is a node, you see? So for every node, I want to make a prediction. And then the value is 1 by 46 by 10. So 46 is the number of time steps, and the 10 here is the number of possible nodes. So I said, yeah, if it is it was only 7, but I think the original data set actually has 8 different nodes. So 8 plus 0 plus 1. So it will have the shape of 10. So how can it select the most probable nodes from each time step? The simple way is to iterate each time step. So let me draw the Y, how it will look like. So since there's only one song, it's like this. It's 0, 0.1, and 0.3, and so on. So this is the first node. And for the second node, it's 0.1, and 0.9, 0.01. So for the second one, and we have 0, 0, 0, 0, 0. So we have altogether 46 time steps. So I'm going to iterate from the first one and second one, third one, up to the 46th one. So that's the meaning of this for loop. So for I in range of Y shape 1, and Y shape 1 is this number, 46. So in this way, even if I change the input song, I can always make exactly the same number of time steps. And then there is a function, which is another random function, TF random categorical. And that categorical takes a sample from take a sample with this probability. So maybe the last node has a probability of 0.999. Then it is very probable to select this one as the final one. But in this way, you can make a little bit variety of your music. Not just to select the most probable one, but maybe you can select the next, the second probabilistic one as your output. So that's the meaning of TF Keras categorical masked one. Oh, okay, yeah, I did not say about the masked. And masked is just to prevent from selecting the zero index and the one index. So here I intentionally make the mask 0 and 0 is minus infinity and 0 and 1 to the minus infinity, because 0 is a string. I mean, it's an empty string, and 1 is unknown. So I don't want these two numbers will be selected. So make some numbers and then add that number to the original one. So maybe you can think, as this one. So this is our first output, but I said there's a minus infinity, and all the others are 0. And then add these two, then these two numbers will going to be minus infinity. There is no chance to select 1, 0, or 1 from this probability. So this is the way we prevent something, and then put the output, and then we need to translate it into F2. And you know you should know what F2 means, and then do something, and then put it into the temp and decode and save it to my list and make it a music. So let me try. Okay, let me listen to my composed music. I don't think it's from Bach. Oh, there is a question. Oh, sure, you should get the different melody from mine. The first, when we train the network, the WX, when we train the network, WX and WH. So do you remember the formula? WX times X plus WH times H. And actually there is a B term, bias term, and actually there is a 10H. But all the other things are, the essential part is here. And these two are randomly initialized. That's the reason why your melody is different from mine. And then the second reason is that once we predict everything, we set TF random categorical or something. So that means in the final, from the final output with 46 distributions, we select different nodes, not totally randomly, but according to the probability. So that's why yours are different from mine. Yeah, so you have to make it in a MIDI file and submit it. But now you can make a music. So why don't you make it a little bit more nicer? Okay, so how can I make it a little bit nicer? So first thing that I can try is to increase the number of epochs. So I just did it 2. It's not, it will not be so good. So maybe I can set 20, and it's pretty fast, but you can see, as you can see, the loss here, it is not decrease, it does not change too much. That means your model is not trained. Why it does not be trained? That's because I said it one here. That means every time you listen to a new note, the information that will be transferred to the next state is just one number. So instead of just one number, I can say it's just 124. I mean 1024. So it's lots of information. So maybe I can define a model and compile and fit it. And this time, I can see the number. It was 2.4, but it's going to be 0.0. But there is no exact match between the loss value and the beautifulness of your song, but smaller loss means usually good. So I'm going to predict and then make output and then listen to the music. I think this is much more like Bach. So let's go back to, what was the original song? So it was. It was the original song, but I think the new music is much more like the real Bach. I guess. You may not agree with me, but yeah. The length limit. Okay, another length limit, 1 minute. So in order to make 1 minute, you need to find a music that has at least 1 minute long. So there is a length limit. Actually, this assignment is going to be your last assignment. I know there is 12 assignments in the next week, but I'm gonna make it to excused. So you don't have to worry about the next assignments because the final competition is already announced, and focus on your final competition. Yes. Yeah, but basically, you're right. Yeah. So in this way, we can do a lot of things. For example, sometimes we want to make a fake image, then you can do something similar to this one to make the fake image, that kind of things. But the fake image is usually not accepted these days. There is no guarantee that even if you have a bigger epochs, there is no guarantee that your song is more beautiful. So there is another way to explore the RNN because, okay, I said it's a simple RNN with this number of layers. And I'm gonna reduce a little bit smaller. But I said, there is another RNN layers. And then I said, that's the, say, LSTM. So let me try this one and compile, fit. The losses not dramatically decreased, but anyway, I have another song produced by the long short-term memory. No, it's not. that good. But there is another possibility, because I can add one more layers. And this time, this is the GRU, it's gated recurrent units. So I don't know yet what it means, but I can run it and then compile and fit. The loss is not that good, but okay, let me, so maybe the number of hidden units was very crucial. So maybe 64. Okay. I don't think why this is not TF keras layers simple RNN. Okay, yeah, again, the lots of hidden dimension. You see the problem. Okay, if I want to stop here, oh, there is an error. Compile. Then it says, oh, I cannot do that because you did not return the sequence. So that is actually the more advanced part. So how can we use the previously learned state to the next training, and that kind of thing is a little bit harder. So I just wanted to stay on the easy one. So let's say just, yeah, true, compile, fit. This is getting worse. Okay, I don't like the LSTM. Not so impressive, but let me try. Yeah, not that bad. So yeah, why don't you try, yeah, something different? So in this case, the normalization will not work. So remember that the normalization, in order to appropriately use the normalization, you have some two different scaled values. So for example, there is a weight in kilograms, and there is I don't know. Yeah, but in this case, we have just a one sequence of nodes. So even if you normalize this, it will not help you much. So, and as I showed you, yeah, increasing the epoch might not help you, and sometimes increasing the number of hidden layer, the size of the hidden layer will help you, or add some more layers. Okay, yeah, but why don't you try something creative? But it's okay. Yeah, 1 minute. Yes. 11 assignments plus pass on the final is A plus. But since I give you all the credit for the next one, yeah. So you're in the 12th assignment is already fulfilled. And this is, yeah, correct. So you have 11 assignments and at least 11 assignments, yeah. So if you have 12 assignments, yeah, that'll be better. But can I give you a better than A plus? Yeah, the 12th assignments is all pass. So I'm gonna give you all pass scores for the 12th assignments. Yes. So this is the problem. So when you go to the final project, there is a time sequence data, and your job is to classify the time sequence data, whether it belongs to the first class or it belongs to the second class. And since this problem is so easy, if you do something similar what we did today, you will get 89% accuracy. So I impose a restrictions. If your final answer does not go over more than 99% accuracy, you are failed. So your final prediction is not over 99, then yeah, you are gonna get a C. Yeah, sure. Music tuning on corpus library. Yeah, you can find the music that is longer than 1 minute. Actually, it depends. If your model, yeah, if your model is not good, then yeah, increasing the epoch does not help you at all. But even if your model is good, increasing too small epoch, it's not to say that definitely, but too small number of epochs is not good, because you can decrease your loss some more. So if your model is bad, then yeah, the epochs wouldn't help much. Yeah. Oh yeah, in that sense, yeah, you're right. Yeah. So it's usually, yeah, we say something like the garbage in, garbage out. So I said, yeah, is not directly measurable. So even if the losses is not so low, you may feel that your generated music sounds good. So so this is the problem with the beautifulness. So how can you measure the beautifulness? The measure we use is how much we can replicate the original music. That is the measure, the loss we are using now. So the beautifulness is something different. Then why don't you try your song? Yeah, you can write your song and then train your melody to or new song. Yeah, because I want you to think about it a little bit more about this one, because this is just a list, your music. So if you want to add some more numbers, then that is going to be another music. Oh, sure. Yeah. Yeah. Oh, it's already. Yeah, I will. Yeah, talk about the final competitions very briefly today. And then next week, there will be no new materials. There is no new concept to cover. I'm just gonna talk about the final competition for the next week. Yep, yeah. So it's similar, but not exactly the same. Yep. So all you have to do is make your own music and then save it to MIDI. And before you submit your MIDI file, why don't you listen to your MIDI file? And even I found a way to, even if you don't have the MIDI player, you can always go to the Google and then search for the online MIDI player. And there are lots of websites that provide you online MIDI player. So if you click your MIDI file to their websites, then they play your MIDI file for you. So please listen to your MIDI file, yeah, and then submit it. Okay, yeah. I'm with you. Okay, yeah. No, the final is not a sum. It's a classification problem, and it's a. So you may think the final project in this way. So there is a sequence of stock prices, and then your prediction is going to be, do you want to buy it or sell it? So if you are successful, then you're going to be rich. So that is the meaning of the final competition. So we have a time series data, and we want it to classify in two categories. So if you are successful with your final competition, you may try to get some stock price data. And then, of course, you have to do some manipulations for the stock price, and then apply your model to predict the future. And if you are successful, then you're going to be rich. Oh, yep. Oh, mobile phone, Samsung player. Yeah, but my phone is not Samsung. Okay. Okay. Oh, I have. Oh yeah, the final project, you have 20 submissions per day. So, okay, I'm going to talk about the final project. So there is certainly the number of submissions. But since I require you more than 99%, and that number cannot be verified until you actually submit your submissions. So sooner you start, you'll get a better chance to submit a lot more. So maybe you have just one more day left before the due date, and then spend all your 20 submissions but cannot get the 99%, then you are gonna see. Oh, sure. Yeah, for the doing your final project, yeah, you can ask me all about your programs and how can you do that. But yeah, I will help you, but I cannot answer your questions like, oh, how can I solve the final project? Well, that's your job. But if you are stuck with some errors, or you are experimenting with the neural network, and then you get stuck, then I can definitely help you. Okay, so let me briefly tell you about the final competition. So final competition is launched, and the due date is this one. And it's on here. So it's a Kaggle competition. And this competition is for you, for this class only. So I know, yeah, there are some students who are taking my other class, but the problem is different. The setup is the same, but the problem is different. So do it separately, because even if you get 99% accuracy here, there is no guarantee that your submission is also get 99% for my other class. So just remember that. So the description is you can use any models, but actually, we just learned a regression model, the convolutional neural network models, and recurrent neural network. So you can use anything you want to achieve the 99% accuracy. So the evaluation is the accuracy, and you should get more than 99% accuracy to pass this final. And the data set is 3, as usual. So it's a test.csv. So it has ID, and the total number of column is 142, but actually the first one is ID, and it has 140 time series data, and then final one is the answer. So what I mean by answer is that details. I cannot go yet to the right, but at the final column, there is a 0 or 1, 0 or 1, that kind of things. So you are training your model, whether it is a regression model, convolutional neural network model, or recurrent neural network. So once you train your model, apply your model to test data set. And this test data set has ID and has 140 data set plus 1 ID. So it does not have the output, of course. So for the output, you have to predict your output and then submit it. The sample submission file is in this form. So ID 0 is, your prediction is 1.0, for the 1, it's 0.0. And if you, since this is the randomly generated sample submission file, if you submit this one, you will get a score of 0.51, which is fail. So you should get more than 0.99000 or 0.99, So this is your competition. I'm not sure you'll be fine or not, but you have to try. So final project is now announced. So I can help you here to do your project, but this is the project. And one more thing that I want to say is that your submission, I'm gonna say this one in the next week also, but once your accuracy is more than 99%, take a picture and then submit to the assignment here. And as soon as I finalize your submission, then I will let you know the grade, the letter grade, based on your whole assignment and your final project. So maybe you can finish it by tomorrow, then you'll get to know whether you get an A+ or not. Even we did not start the final, so you'll get your final grade. So please do it as soon as possible. Okay, that's the end of today's lecture. And actually, that's the end of the whole lecture. And there is no more new concepts to be explained. So all I'm going to do is just listen to you, watch your questions. Okay, why don't you try this one and this one, that kind of things. No, final column is the output. The first column is the ID. Yeah, we are going to have a Zoom meeting next week, but I'm just answer your questions, and then I'm going to explain the meaning of the competitions, and probably it will, I don't know, it will not be so long. So we have a Zoom meeting next week. Yeah, that's right. Yeah, you need to use 140 columns to predict the final column. That's right. Next 2 week is not optional. I give you the full credit for the 12 assignments. So that means your next 12th assignment will be exempt. So why don't you publish your music? Yeah. Okay, thank you for listening, and please enjoy your music, and then let me enjoy your music too, and have a nice weekend. See you next week.